Assalamualaikum and good afternoon. My name is Muhamad Akashah bin Roky. My metric number is B0517101885 and my supervisor for this project is Puan Ruzy Haryati Binti Hambali. The title for my project is The Effect of the Thermal Responsive Material Polymeric Filament to Strength and Transformation in 4D Application. Let's start this presentation on the introduction of this project. 4D printing works as a new design of a complex spontaneous structure that which add the change of shape or properties over time to conventional 3D printing. The element of 4D is 3D printers, external stimuli, response material, interaction mechanism, and lastly, mechanical modeling. Smart materials are materials that are manipulated to respond in a controllable and reversible way, modifying some of their properties as a result of the external stimuli. And lastly, the thermal response SMP make transformation by thermal stimulus from a temporary shape to its inherent permanent shape. We continue to the problem statement of the project. As stated by Zhang on 2019, conventional 3D printing technologies focus on fabricating static structure from a single material which cannot meet all the demand of dynamic function needed for applications such as soft gripper forgery, safe 4D packaging, and adaptive wind turbine. But an efficient 3D printed 4D method was developed by using a single thermoplastic polymer without a shape memory function. It is said by GE et al. On 2016. And a single thermoplastic filament that have no shape memory effect can be used to perform the 4D material but not as efficient for 4D printing application. It's said by Ku et al. On 2015. And lastly, the difference in thermal deformation of exposing the part in different temperature will cause bending deformation on the part. For the objective of this study, first objective is to study the various transformation and polymeric filament of smart material in 4D application, focusing on the thermal responsive of the material. Next objective is to fabricate the thermal responsive 4D smart material printing parts, and last objective is to determine the tensile strength of the thermal responsive 4D printed part. Let me continue to the scope of project. First scope of project is extensive research, design and printing 4D part using PLA plus wood and thermoplastic polyurethane or TPU that have thermal deformation in response to thermal stimulus. And apply additive manufacturing technology on fabricating the test specimen and 4D printing part by using fused deposition modeling or FDM. Examine and analyze the transformation of the smart material response to the temperature applied on the printed part specimen by exposing on the temperature 60 degrees Celsius, 100 degrees Celsius, and 140 degrees Celsius. And last scope is to determine the quality of the 4D specimen focused on the strength of the printed part by using ultimate tensile machine. Follow the standard STM D638. This is the detailed review from the previous study. This part will cover the method to complete this project. Hopefully, this project will cover the research gap between this study and the previous study. Now I will talk on the methodology of this project. This project starts with the identification of problem statement, objective, scope, and research significance. Then I continue this project on the literature review, stimuli, response, natural smart properties, and 4D printing. Then we go to the design of the 4D part using SolidWorks software and fabricate the part using FDM machine. And this will cover the objective too. And then we check either the print have error or not. After that, we apply it on the in the oven, and then we examine and analyze the product that we applied, and then we continue to do the tensile test on the part. This will cover the objective 3, and lastly, we have the result and we discuss and analyze the result. We continue on the methodology part. The raw material for this project is PLA plus wood filament and thermoplastic filament or TPU. Then we go to the CAD model. As you can see, the CAD model of this part has the U shape, the curve on the middle. This is because to focus on the reaction area, and the reaction we want is to make it U shape. The thin design is made because we need the fast reaction from the specimen itself. Then we fabricate the tensile specimen, which is the tensile specimen compiled to ASTM D638 Type 4 standard for PLA plus wood. And for the specimen on TPU, we follow the standard of ISO 5272. This because we use different standard because on the different type of material. The PLA is polymer and the TPU is a rubber material. To continue on the methodology part, we move to the fabrication the specimen. First is the 3D printing was executed using Enders 5 Plus. As you can see on the left, there is a picture of Enders 5 Plus machine and the printing process of the specimen. We have different parameters for each material. As you can see on the PLA plus wood, the print temperature, bed temperature, size of nozzle and print speed is different, but the field density is same because we want the same field density to test. As you can see on the right side is the specimen that have been produced by using the Ender 5 Plus. Next step is on the exposing the specimen to heat, which is heat treatment. We expose the specimen on the heat and by sinking the specimen in the oil to avoid the surface of the material affected by the heat. Then we place in the drying oven. The parameter temperature is set up on the oven which is 60 degrees Celsius, 100 degrees Celsius, 140 degrees Celsius. And the deflection of the material shape change is recorded. This is the video. But due to the limitation of maximum 2 hours entering the lab, the limitation recorded tool, we have to record the results by manually. But we maintain the earlier agreed experimental plan. As you can see, after 5 minutes, there has the detection of the part. This is sample on temperature of 140 degrees Celsius. Okay. The last part on the methodology part is the tensile test that has been performed by using Shimadzu AGSX tensile machine. This tensile machine takes place by using different parameters on each material, and the tensile curve has been plotted consequently. Then we go to the deflection measurement that I've measured on the deflection measurement, which as you can see the first and when with the material straight, and we will measure the deflection, the length reduced after the deflection itself. This presentation continue with the result and discussion. The deflection of the material has been recorded after the heat applied on this. The heat is applied for 5 minutes. As you can see on the left side, there is a first original size of the material before having placed into the heat. As you can see, the average of reduction is 57 mm and 58.5 mm for the response on 60 degrees Celsius. This shows that 5% of deflection shown by PLA plus wood and 2.5% shown by TPU. For 100-degree heat treatment on this specimen part, did show that it takes more deflection on this part, which is 4.5 average and 6 mm average on the TPU. And it showed that 7.5% for deflection on the PLA plus wood and 10% that have take place the deflection by the TPU. And for the third temperature that have been applied on the specimen, which is 140 degrees Celsius, we can see the largest of the deflection happened for this part, which is 6 mm take place on for the PLA plus wood and 9 mm that have been changed from 60 mm that have been take place by TPU. And it shows 10% deflection happened to the PLA plus wood and the deflection happened for the TPU is 15%. From the responsive result, it showed that the higher the temperature of heat applied on this specimen, the higher the percentage of deflection produced by the material itself. Continue with the result and discussion on the analysis of max force result. From the bar chart that have been produced, it showed that 592 megapascal for the PLA plus wood to before it break, and the max force for the TPU is 292 megapascal. To compare with the previous study that have been taken from the Ku et al. On 2015, the max force needed for PLA need is 500 until 580 megapascal, and the tensile force that need for the smart material polymer, which is the max force needed for the smart material polymer is 250 until 350 megapascal. It shows that this printed part that has been printed by this project is still in the range of the max force result. Continue on the result and discussion we continue to the strain stress curve that we obtained from the tensile test. As you can see on the graph, I have set the range for the tensile strength that produced by PLA and the range for the tensile strength of the SMP that we obtained from the previous study and also the manufacturer itself. From the graph, the strength tensile of the PLA plus wood is 25 Newton, while for TPU is around 27 Newton plus minus. Based on the tensile strength analysis, both materials produce tensile strength in the range of the tensile strength produced by the normal PLA and also smart material polymer, which is the tensile strength for PLA is 21 until 40 Newton. This is referred on the Ku et al. On 2015, and the tensile strength for smart material polymer is 15 until 40 Newton. That I've been referred on the manufacturer e-sign itself. As a conclusion for this project, the objective one, which is to study the transformation of the polymeric filament on thermal responsive, was successfully carried out. Next is the polymeric filament can respond to external stimuli, which is thermal, same as smart material itself. However, the temperature needed for the material to respond is quite high compared to material of smart material, which is 45 degrees Celsius until 90 degrees Celsius for its material to react. And the third is for the second objective. The fabrication of the thermal responsive material that have smart properties can be printed by using FDM machine. And the last conclusion is the tensile strength of the thermal responsive for the printed part is same range of the tensile strength of PLA and shape memory polymer itself. This shows that the other material also can respond to thermal stimulus. As a recommendation, the further research on the thermal responsive material can be done to other material that recently used in additive manufacturing, such as ABS, PETG, and the other materials. And continue the study on how the responsive of the material that have react when we apply the heat to the material again. And lastly, the printing process by using 3D printing machine that has no enclosure also might affect the printing result. Therefore, it is suggested to add the enclosure to 3D machine or using a closed door 3D machine itself. That's all from me. Thank you.